Hello, welcome back. So today we're going to be talking about division lemma. All right, so as you probably guessed, it's a lemma. So let's talk about what the lemma states. Okay, so for any integers n and m with m not equal to 0, then there exists unique integers k and r such that we have this equation, n equals km plus r. And there's a little bit more, where 0 less than or equal to absolute value of r less than r. Sorry, r is positive. or non-negative, because it could be 0. Absolute value then. Okay, cool. All right, so let's read it again. So some evil scientist hands you two integers where one of them is not 0. Then you can produce a unique, so that means there's not like multiple ones that you could pull out. There's one pair and one pair only of integers k and r, such that your one that could be 0 is equal to k times m plus r. And then here's our restrictions on r. So that is actually where the magic lies in it being unique. Okay, because we're forcing r to be non-negative. So r has to be 0 or positive. Okay, if we allowed r to be negative as well, then we would at least have one other option. We would have two options every time. If we let r be anything even bigger than m, then we'd have quite a few options for k and r. Okay? All right. Okay, so this probably doesn't look super familiar, but this is actually a concept that you are familiar with, but maybe just didn't know you could write it like this, or at least haven't thought about it. So first, let me make a note. R is often called the remainder, and if r equals 0, m divides n. So maybe that seems weird, but the definition kind of gives it away, the remainder part. Because remember, if you divide two integers, you have a whole number plus some remainder. Okay? Well, if r equals 0, then they perfectly divide each other. The other way that you can see that, if what I just said sounds like a bunch of gobbledygook, is you would end up having n equals km. K is an integer, so by definition, m divides n. So that's just by our definition of division. And remember, m's not allowed to be 0. Okay? Fabulous. Let's move on. Okay, so this statement here, this division lemma, is extremely, extremely useful. So you can use it on any two integers where at least one of them is not 0. Okay, so when you have a problem where you want to use it, you want to pay attention to what number you care about. Then that will likely be. So let's do an example. And so same type of deal. I'm probably not going to just keep rewriting the division lemma, but if you are going to use the division lemma, you need to somehow state it somewhere. So I'll show you in this example. I'll do an example of that. Okay, let n be some integer. Show one of n plus 4, n plus 8, n plus 12, or n plus 16 is divisible. Okay, so that's our question. What number do we care about? So a lot of people will usually say, well, I guess also n plus 4 and 8 and 12. So maybe we care about 4. Oh, but n doesn't have anything to do. So the number that is constant throughout this is 5. We want to see if these are divisible by 5. And also, the other thing that gives it away is, remember, we can tell if m divides n if r is 0. So maybe we want to use division lemma on this and show that our unique things that we get, there's always at least one of them that has the remainder as 0, so that 5 divides that number. Okay. So 5 is going to be our m. Let's start the proof. Okay. So here's my example of stating what the division lemma is. Well, kind of. So here's what I'll say. By division lemma, we know there exists unique k and r in the integers such that, and now we're going to write it out. So n equals 5k plus r. So some of you might be protesting right now, and rightfully so, that I'm talking about just n. Well, Danica, we need to think about n plus 4, n plus blah, 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 blah. But now that we have this, we can always just add 4 to it, or add 8 to it, or add 12 to it. Okay, so this is kind of our baseline right now. Okay, and then we can always add things to it and see where that takes us. Okay, but I hope some of you are realizing I forgot something from the division lemma. What's missing? R restriction on R. Okay, so see, so it doesn't always have to be super formal when you state the division lemma, but you definitely want to use the words division lemma. You don't want to just like all of a sudden be like, well, there's this K and R, blah, 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 blah. You want to be able to, you want to show people that you know what you're talking about. Where 0 less than or equal to R, less than 5. Well, 5 is already positive, so we can just write 5. We don't have to write the absolute value. Okay? All right. So, all right, we know that if 5 is going to divide one of these things, then the R is going to have to be 0. Well, let's think about what all of our options are for R. Try to say that's 7 times fast or whatever, 5 times fast maybe. Okay. Well, R is an integer, and R is between 0 and 5, not including 5, but including 0. So we have 5 cases. So first, we have when R equals 0. All right, so what happens then? Then n equals 5k. Sweet. So 5 divides n. Okay, well, the statement we're trying to prove is an OR statement, right? So we just need to show that it's any one of these. That 5 divides any one of them. Okay, cool. So done. Check. All right. When R equals 0, the statement is true. Well, how about when R equals 1? Well, then n equals 5k plus 1. Okay, well, we can't say that 5 divides n, but, if I think about, I want it to be 5 times some integer. Well, in order to factor a 5 out of something, it needs to be a multiple of 5, right? So what do I have to add to, what could I add to 1 out of all these options that would give me a multiple of 5? Give you a few seconds. Well, 4 is going to work. So if I think about, so n plus 4 equals 5k plus 5. Sweet. Okay, so now I can factor 5 out of that. Well, k is an integer, so k plus 1 is an integer. So 5 divides, and I like to put these in parentheses so it doesn't look like 5 divides n. Oh, also plus 4. That's kind of weird, but so 5 divides n plus 4. How awesome is that? Okay, let's keep going. How about r equals 2? Then n equals 5k plus 2. All right, let's do our same thing. What do we have to add? What can we add to 2 that makes it divisible by 5? From what we have, right? So we can't just add 3 because, I mean, true, that's true, right? But that's not something we're trying to show. We're trying to show that it divides one of these things. Oh, okay, well, if I do 2 plus 8, that's 10. That's divisible by 5. Cool. So n plus 8 equals 5k plus 10, which is 5 times k plus 2. All right, nice. All right, 5 divides n plus 8. All right, now I'm going to kind of go a little bit faster. All right, 3. Then n equals 5k plus 3. Who could I add to that? Well, If I added 12, now I'm going to skip to factoring out. So 15, so we have k plus 3. All right, so you might be seeing a pattern here now. 5k plus 4. Okay, well, if I had 16, that gives me 20. And remember, there's always a lot of different ways you can do things. It's just, to me, I think this is the easiest way to do this particular problem. Okay, do I need to think about when r equals 5? No, I don't, because r is always going to be less than 5. Okay, so you could like hypothetically think about it, but it's not really going to help a lot. Okay, so did we show what we wanted to show? We said, all right, well, n can be any integer, and one of these things will always be true. And so this might seem weird because it's like, well, Danica, you were picking who r was. Well, what I was really doing was I was saying there's only so many options for r to be. This is kind of like when we talk about, okay, well, the integer has to be even or odd, okay? So no matter who n is, r has to be 0, 1, 2, 3, or 4. So if it's 2, then you would look at n plus 8. Okay, if it was 0, then you're done, n. 5 divides n. If it was 4, then you would look at n plus 16, etc., etc. So I'm saying no matter what situation I have, I can pick one of those and show that one of those is divisible by 5. Okay? All right. So therefore, we have considered all situations, all possible situations. Let's say we have proven the statement since we considered all possible situations. Okay. So not every single one is going to be like this, where you list out every single thing. But just remember, when you know who you're dividing by, as long as it's a small number, then you can just plug and chug. And it might not always look like this, you know. You might be trying to show something else. You might be trying to show that something always ends up even, or I don't know. There's a lot of things you could. Okay, well, here's a good one. Here, I'm going to zoom in again. Okay. Show for some x, y, z in the integers where x squared plus y squared equals z squared that one of x, y, or z is divisible by 2. So you'll want to remind yourself of the division lemma. And let's jump into the proof. Okay, so, well, how to reveal this in a nice way. Let's start by considering that neither x or y are divisible. Okay. So if they're not divisible by 2, then they cannot be even. Well, the other way to think about it is using our division lemma. Then x equals, say, 2l, because remember 2's our important number here, so that's our m, okay? So 2l plus q, and y equals 2m plus n. I don't know. So the letters don't really matter so much, just as long as you don't repeat them in the same proof. For L, M, N, Q in the integers, and both Q and N are bigger than 0 and less than 2. So that might seem weird. Well, Danica, didn't you say in the division lemma that they have to be bigger than or equal to 0? Well, if either of them were equal to 0, then x or y or y, or whatever, would be divisible by 2, right? Because if their remainder is 0, then they're divisible by their m, which in our case is 2. Okay? Well, that only leaves them with one option. Then q equals 1, who equals n. So they're both 1. All right, cool. Okay, so then x equals 2l plus 1, and y equals 2m plus 1. Okay. All right, so now we kind of feel a little bit stuck, maybe. What were we trying to show? Oh, we're trying to show that z squared now has to be divisible by 2. Okay? because we need that one of these is divisible by 2. We already said, well, x and y, they're not divisible by 2. So now we need to see about z. Okay, z squared equals 2l plus 1. Oh, also, I'm sure maybe some of you out there are thinking, okay, but Danica, since it wasn't divisible by 2, you knew it was an odd number, so like you could have just done that. Well, I'm just trying to use the division lemma somewhere. And they might ask you to use the division lemma, I'm not sure, in like some problem or something. Okay, so let's see, z squared equals, and now let's work it out, I guess. So 4l squared plus 4l plus 4m squared plus 4m plus 2. Well, what in the heck am I even trying to do now? Because I can't just like square root out of nowhere. That's not very helpful. And then plus or minuses, ugh. Okay, but what if I could show that z squared is divisible by 2? Okay. Yeah, I think I could do that because I could pull out a 2 out of this whole thing. All this craziness. Okay, and then this whole thing, that's in the integers. Okay, so then z squared is divisible by 2. Okay. You could, once again, you could talk about even stuff, but I'm going to take a little bit of a different route. Then 2 divides z times z. Okay, all right. This is when things get interesting, okay? Since 2 is prime, then 2 divides z from this first thing, or 2 divides. So that may seem weird, but here's kind of the idea. So let's say 3 divides 12. Well, we can rewrite 12 as 2 and 6. Or we could rewrite 12 as 3 and 4. And in both cases, 3 divides one of them. So 3 divides 6, and 3 divides 3. But this is because 3 is prime that we're allowed to do this. Because let's consider if we try to think about 6 divided by 12. So 6 is not prime. 6 divided by 2 times 6. Okay, well, divide 6. 6 divided by 3 times 4, well, 6 doesn't divide 3, and 6 does not divide 4 either. So that's why it's special with prime stuff. This is a number theory thing. If you want to do a deep dive on it, I would love to talk about this kind of stuff. But anyway, just remember it's special that 2 is prime, okay? So that's why we're allowed to do this. Well, in this case, we're saying the same thing twice. Right? So over here we were saying, well, 3 divides 2 or 6, or 3 divides 3 or 4. And then we just knew what it was because we knew what all the integers were. But here we're saying, well, 2 divides z or z. That's the same thing. Therefore, 2 divides z. Now we're done. Okay? So if 2 does not divide, so remember that's what this symbol means. It does not divide x, and 2 does not divide y, then 2 divides z. All right, well, do we have to keep going? Actually, we don't, because if 2 divides x, we're done. If 2 divides y, we're done. Okay, but if 2 doesn't divide x or y, we're done, because it divides 2. If 2 divides z. Okay, so it's actually pretty cool. So either, well, at least I think so. So either 2 divides x, y, or inclusive. So maybe it divides all of them. I don't know. Okay, maybe we should say like if x squared plus y squared. All right, have a great rest of your day.